Hello everyone, I am Niyar Kadas along with my teammates Kemal Shah. We will be presenting our project CardioBeat AI. This project explores how we can use deep learning automatically classify heart sounds with the goal of making a diagnosis faster, more reliable and more accurate. Let's start with the problem. The problem that diagnosing heart sounds. Heart sound analysis is a critical step in identifying cardiovascular disease. In traditional methods, doctors rely on stethoscopes to listen for abnormalities like murmurs or valve defects. But this method has several challenges. It is subjective. Different doctors may interpret the sound differently, and it is time consuming, and it is prone to human error. So these limitations highlight the need for an automated AI-based system that can provide consistent and early screening. So we build a solution using a deep learning model, deep learning that automates heart sound classification, providing a potent tool for preliminary diagnosis, improving efficiency and accuracy. And our goal is to build an end-to-end system that can take a heart sound recording and accurately classify it into one of several predefined categories. Let's move into dataset. To build the system, we trained on a dataset of five classes of heart sound, like AS, MR, MS, MVP, and normal. Each classes contains 200 samples, giving us a total 1000 recordings. The dataset is well organized into folders, which help in training and evaluation. So, in our data processing sequence, we first download, then unzip data, uh, then we make the data in separate folders and we train the model using this level data. Then move into process funnel. And our system follows a straightforward pipeline. First thing, the user uploads a heart rate recording such as a WAV file, MP3 or MP4 file. Then our model clean the signal, apply bandpass filter, and extract MFCC feature which capture the unique sound pattern. Then we train the deep learning model by using these features as input in CNN, which learns to identify patterns in the hardware. Then our model predicts and the system outputs the classified condition along with the confidence score. This is the end-to-end funnel transforms a raw hardware recording it on actionable prediction. Then move into solution features. Our solution offers several key features like a simple and user-friendly interface for uploading hard sound. Like it supports for multiple formats, not just WAV. It supports for MP3 and MP4 also. Then it gives a real-time visualization of waveforms, of spectrograms, making the process more engaging. Our model gives an actionable output showing both the predicted condition and the probability distribution across all the classes. This ensures that the tool is both technically robust and easy for experts to use. With this, now my teammate Hemel will take you through the further step. Over to you, Hemel.
Thank you, Niharika. So now I'll be covering the impact of the solution. So basically, our impact has these four pointers. So it basically bridges the technology it bridges the technology and medicine. So technology is used to predict the heart disease. So this is how it connects the both of the domains. Then uh, empowering users has the UI and our near perfect solution for the models. Then this is the overview of the impact. Then I will be covering the standard areas as well. So how our model is different from other solutions. So broad accessibility. So you can access the app from a smartphone, tablet, or a computer. Our UI is compatible for all of these devices. Then empowering visuals. So basically we have the sound wave and spectrogram for visual basis as well. Then real world utility basically means that we have a very broader future scope. So the users can rely on our app very uh, seemingly well. And flexibility input allows the users to have a very broad amount of video formats like audio and video formats like MP3 and MP4 and WAV files as well. So after that, the architecture diagram involves the audio input as the first step. The user gets three options as the extensions, and then the pre-processing and feature extraction takes place where the main part of the audio is captured, and then it is basically predicted using the CNN models, which analyzes the spectrogram and the sound waves as well. Then finally the output is shown over here in the Streamlit page. Then the interface preview, as I mentioned that there is the sound wave of the user input. So the user has input as a user inputs an MP3 file over here as an example, and there is a sound wave with the timestamp and the uh, amplitude as well. And there are two models from which the user can choose. One is made by me and one is made by Niharika, my partner. And then here is the spectrogram with the results. So as you can see over here that the results can be downloaded as well with in a CSV file with the probabilities. And that was the user side interface, and this is the admin side interface which me and Niharika manages. Here we can see the daily usage thing, the total predictions, overview, the data management and analytics thing as well. Then there's the future scope. So as I mentioned that there is a last future scope as well. So the live audio input is a feature which we are looking up right now. We are working upon it right now that the user can basically use this stethoscope or many other sensors as well for the live audio input. We will connect it with the device later on. And then mobile app development is basically an app for Android and iOS as well. Then database integration allows continuous training to improve the model. Then there's expanded classification where heart conditions and abnormality classes can be added later on. And that was our project, guys. Thank you so much for listening.